So within module 6.2, we're going to continue looking at pure bending. Now within this module here, we're going to look specifically at plastic deformations, then take a look at some elastoplastic materials and some eccentric axial loading. And with this loading here, we're going to take a look at stresses, both axial and bending stresses. Then we're going to take a look at the last section here for unsymmetric bending and bending of curved members. So within this module, we'll go over some of the key theories, talk about the governing equations, apply some practical applications, and then go through some problem-solving techniques as well. So the first topic we're going to take a look at here is plastic deformations. So within this here, what we want to do is reference back to our textbook to equation 410. So within 410, what we can see here is that for any member that's subjected to pure bending, we have this following relationship right here. So this is saying our strain in the x direction is equal to y over c times E sub m. So what this says is now that our strain varies linearly, so we can see this is going to vary linearly across the section right there. So what is our y, what is our c, what is our epsilon x and epsilon m right there? Well, we can come back over here to our diagram over here. We can see, okay, there's our x axis right there, so there's our strain along our x-axis right there. We go up to the outer surface right there, so that's our c value, is that distance at the outer surface right there, and our y value right here, it varies along our y-axis right there. Then we can see we have our max strain right down there at our outer surface of our object right there. So that relates to the variables within equation 410. So now if we consider the case where we have a material that, or a member that is made of a linear elastic material, then the neutral axis passes through the centroid section. So for that there, we then have this reduced equation over here, that sigma in our x direction right there is equal to negative my, our moment, times that y direction right there, all divided by I. And again, I is going to vary based upon the shape and geometry of our member. Now for a member with a vertical and horizontal planes of symmetry and a material with the same tensile and compressive stress-strain relationship, then the neutral axis is located at the section centroid, and the stress-strain relationship may be used to map the strain distribution from the stress distribution right there. So we can come down here and we can see our two other graphs here. So now we have in figure 4.28, we can see here's the material with nonlinear stress-strain diagram right there. So we can see this is how it would react right here. We have our strain in the x direction. We have our stress over here. So this is our stress-strain diagram right there. And as we're coming up here from our center point right here, we can see, okay, at this point here, we have our E sub m right there, our max strain right there, and then we have our sigma max over here, or our max stress right there. We can join those two together at that point in the curve there. Then we can come down to figure 4.29. Now in 4.29, what we have here now is we can see there's our sigma x over here and our y value up there. There's our c right there. So this is nonlinear stress distribution in a member under pure bending. So a couple key factors right here. This is our stress distribution, and we're looking for this under pure bending right there. So with that there, we can see as we get out towards our max right here at the distance c away from where we're at our outer surface of the member right there, the negative c down there. We can see down here now we have our sigma max right there for our max stress located down at that location. So now the next topic I want to discuss is plastic deformations. So as we're discussing plastic deformations, one of the things we want to think about here is that when the max stress, or maximum stress, is equal to the ultimate strength of the material, failure occurs, and the corresponding moment, our mu, is referred to as what we're calling here our ultimate bending moment. So there's a new variable right there. M sub u is our ultimate bending moment. Now, the next thing I want to talk here is our R sub b. Now, R sub b is the modulus of rupture in the bending. And this is found from an experimentally determined value of that mu, or our ultimate bending moment right here, and a fictitious linear stress distribution. So we can see the relationship between our modulus of rupture and bending, our RB, and our ultimate bending moment, mu, given in equation 4.32 in our textbook. So RB is equal to mu times that c is again at the outer surface right there, divided by our polar moment of inertia here, our I value right there, and again that will be determined based upon our geometry of the member we're talking about. So now another thing to discuss here is that RB, that modulus of rupture and bending, may be used to determine our mu of any member made of the same material with the same cross-sectional shape but different dimensions. Then we can go back to that same figure 4.29 that we looked at before over here, and we can see our nonlinear stress distribution in a member under pure bending right there. So that's the same figure we talked about before on the previous slide. And then down here, what we can see is we compare this to 4.30, now where we have here a member stress distribution at ultimate moment right there, MU right there. So we can see as this goes out here to this RB value right here, now we can see this linear line right there going along there. And this again is our stress in the x direction and our y-axis right there. And this right here is our outer surface at that distance of c, as we can see in the above graph. So now we're going to take a look at members made of an elastoplastic material. So within this here, the first thing we're going to take a look at is a rectangular beam made of elastoplastic material here. So this relates back to equation 4.15 in our textbook right here. For the case when our sigma sub x is equal to or less to our sigma sub y right there, we have our max stress right here, our sigma sub m is equal to our moment times that distance c, where our distance c is the outer surface right there, divided by our polar moment of inertia I right there. So from that there, what we can see now, well, our sigma m will be equal to our sigma y right here, where this is equal to, now our my is equal to a relationship to our sigma y from equation 4.33 in our textbook. So our maximum elastic moment, m sub y, is equal to I over c, right there. So there's that ratio, and a lot of times we're going to leave it in the form of that ratio, and we'll see why later on, right there, times our sigma sub y right there. Now, with this relationship here, if the moment is increased beyond this maximum elastic moment right there, which is our m sub y again, then the plastic zone develops around an elastic core. So we're going to want some information about this elastic core. Now, elastic core, we're denoting this by the variable y sub y right here. So this is our elastic core, but keep in mind that this is the half thickness of our elastic core right there, so that there will be two of those for the whole elastic core. So this is just half it right there. And this relates back to our equation 4.38 in our textbook, where this is saying that our moment is equal to 3/2 our my, or our maximum elastic moment right there, times, now in parentheses we have here 1 minus 1/3 times that elastic core, our y sub y squared, over our c squared, where again c is that outer surface of our member right there. Now we want to know, as this moment increases right here, the plastic zones expand, and at the limit of deformation is fully plastic. So at that limit, it is going to be fully plastic right there. And we have this relationship shown by equation 4.39 in our textbook right here. We have that our m sub p is our plastic moment right there. M sub p is plastic moment. And this is equal to 3/2 our m sub y, where again, our m sub y, defined up above here, is our maximum elastic moment there. So our plastic moment is 3/2 of our maximum elastic moment right there. So again, this is from equation 3.49 relating back to equation 4.33 in our textbook there. Now, another thing to consider here, this ratio between the plastic moment and our maximum elastic moment right here is what we're calling our shape factor. And this shape factor is denoted by the variable k right here. So k is equal to m sub p, where m sub p is that plastic moment, divided by m sub y, where m sub y is that maximum elastic moment right there. Now, a thing to note about this is going to depend only on the cross-section shape, so the shape of that cross-section there. Now, this derivation, we can go through this in detail a little bit more on our textbook if you're interested in how we came up with these relationships here. And this derivation is on pages 275 to 277 of our textbook. So now if we'll take a look at this figure over here on the left, we can see what we have here. We have the bending stress distribution in a beam 4, and we can see in part B up here, this is for the yield impending when m is equal to my. So again, that's for the case where our moment is equal to our m sub y, or our maximum elastic moment right there. Then we have part C right down here. We have our partial yield, where our moment is greater than that maximum yield, maximum elastic moment right there. So that's what we have down here in part C. And in part D, we have this as fully plastic right there, where we have our m is equal to our m sub p right here. So this is the case right here where m is equal to m sub p right there in part D. So if we take a look at this part C right here, we can see there's our elastic region right here. So when we're talking about this elastic core, this is what we're going to be looking at right there for our y sub y, for our elastic core right there. And the whole thing would be 2 times y sub y for our equations. So next I want to take a look at plastic deformations of members with a single plane of symmetry. So what we're going to be looking at here is fully plastic deformation of a beam with only one vertical plane of symmetry. Now for this case here, the neutral axis cannot be assumed to coincide with the central axis of the cross section right here. So we can see over here, there's our neutral surface right here. in part A. So this is a non-symmetrical beam subject to a plastic moment right here. Where in part A, up this top part right here, what we can see is we have a stress distribution. So we can see that right there. There's our stress distribution, sigma sub y right there, negative, sigma sub y, positive down here. Now the resultants are R1 and our R2 of the elementary compressive and tensile forces form a couple. So we have these compressive and these tensile forces. They're going to form a couple right here, which are going to be R1 and R2. So R1 is equal to R2. So if we see down here in part B of this here, we have our resulting moments acting at tension and compression centroids right there. So you can see there's centroid 1, C1, there's centroid 2, C2 right there. And we can see that our neutral axis does not coincide directly with C1 or C2 in this case right here. Then we also have, we can see this relationship here, that A1 times our sigma y is equal to A2 times sigma y, where we have A1 is this area up top here, and A2 is the area down there. Now that's just saying that if we take that times that sigma sub y right there from up here, this is going to be equal to this A2 times sigma sub y as well. So what that means with those there, if you think about that, if sigma y and sigma y are the same on both, then A1 must be equal to A2. So therefore, the neutral axis that we can see here, N sub A, our neutral axis right here that we can see forming around here, what this does is it's going to divide the cross-section member into equal areas. That way A1 and A2 must be equal in that case right there. So from that there, what we can see then is we can go to equation 2.79 that we've derived in our textbook here, and the plastic moment for the member, M sub P for plastic moment, is equal to 1/2 area, now we see that both A1 and A2 are the same right there, times our sigma y times D. Well, now what is D? Well, we come back over here, this distance between our two centroids C1 and C2 right there, that is our distance D that plugs into equation 2.79 from our text. So the next topic I want to talk about here is residual stresses. So we're talking about residual stresses. One thing we want to talk about are these different zones here. One zone we're going to talk about is our plastic zone. So these plastic zones develop in a member made of an elastoplastic material, so going back to that topic of elastoplastic materials, if the bending moment is large enough. So that's a big stipulation right there. This bending moment needs to be large enough in order for these plastic zones to develop in this elastoplastic materials right there. Now, since the linear relationship between our normal stress and strain applies to all points during the unloading phase, then the unloading phase can be handled by assuming the member to be fully elastic. So this is one of the assumptions that we're going to make with this here, is that this is going to be fully elastic. So this leads us into that topic of our residual stresses, where residual stresses are going to be obtained by applying the principle of superposition to combine the stresses due to the loading with a moment M, right there, our elastoplastic deformation, and our unloading with a moment negative M, which is our elastic deformation right there. So we can see our elastoplastic deformation and our elastic deformation by M and OM by those two moments for loading and unloading. Now, in general, this final value for our stress is not going to be equal to 0. So now we can come over here to figure 4.37 and take a look at this within this graph here for our stress strain curve. So we have our strain down here in the x direction, our stress up here in our x direction right there. And what we can see here is the elastoplastic material stress strain diagram with loading and reversal. So we can see here we load it up here along this line up until our sigma sub y right there. And then we come across, there's our yield stress right there, come across right there, and then we unload it back down here until we get down to our negative sigma sub y right here. So this is with loading and with unloading in this diagram right here for an elastoplastic material. So now let's take those concepts, theories, and governing equations we just saw in the beginning of this module here and apply it to an actual application. So we're going to take a look at our concept application 4.5 and 4.6, and I'll go through my hand solution for part 4.5 of this application right here within the problem. So we can see we have a given diagram over here. We can see we have B is equal to 50 millimeters for the width right there. We can see our C from the center line right here going up to our outside surface right there, 60 millimeters on both ends right there. And then we have the thickness of our elastic region right here, our elastic core right there as Y sub Y. So let's read our problem statement now that we've taken a look at the diagram. Our problem statement tells us a member of uniform rectangular cross section, so we can say this is uniform rectangular cross section there, is subjected to a bending moment. So they give us our bending moment. They say M is equal to 36.8 kilonewton meters. Now this member is made of an elastoplastic material with a yield strength, so they give us our yield strength right here of 240 MPa, and an elastic modulus they give us as 200 GPa. So pay attention to our units. We're in MPa, GPa, and kilonewton meters here. Make sure we do the correct conversions. So for the first part, for application 4.5, they asked us to solve for two things. They want us to determine A, the thickness of the elastic core, and B, the radius of curvature of the neutral surface right there. So we want to find both of those. We'll solve for each of those separately. And then as we move on to the second part, 4.6, after loading has been reduced back to 0, then they want us to again go through and determine part C, the distribution of those local stresses, just like we've seen in a couple of previous slides there. And then again, the radius of curvature for this section here when the loading has been reduced back to 0 there. So from here, now that we've read through our problem statement, taken a look at our diagram, we can create our setup page. So within this setup page here, again, we labeled here, this is a concept application for 4.5 and 4.6. I'll just be doing 4.5 for my hand solution here. So first thing we do is write down everything that they've given us within the problem statement and given diagram. So we can see again, we want 4 different things as we're going through here. We want the variable name, we want the units of the numerical value of it, we want the units, and we want how it relates back to our problems. That's what we have here. This is our bending moment. We're calling it variable M right here. Value is 36.8 kilonewton meters. And then we have our yield strength over here. Sigma sub y is 240 times 10 to the 6. Now notice, converted this to pascals for this here. Same with our modulus of elasticity, E. This is equal to 200 times 10 to the 9th in units of pascals right there. Then we have our distance right here, our C value right there, 60 millimeters. Now I've gone ahead and converted this to meters because I realize everything else is going to be in meters as well. So this is 0.06 meters. And I've done the same thing for our width here, B. B was given to us as 50 millimeters or 0.05 meters right there. Plug those in. Now the next step is to figure out what they'd asked us to solve for. So in this problem here, they asked us to solve for 2 different things for part 4.5 right here. The first thing they want to solve for in part A was the thickness of that elastic core. Now this is 2y sub y because if we recall, this y sub y right here from our diagram right here is only half the thickness. If we want that full thickness, it's double that right there. So that's why it will be 2 times our y sub y right there when we add those two together. And then the second thing they asked us to solve for in part B here was the radius of curvature of the neutral surface right there. So this is our rho variable right there that we'll be solving for. So now that we've had the opportunity to read through the problem statement, look at the initial diagram, and create our setup page, we can now reference back to that to figure out what our governing equation is and our procedure for analysis. So let's start with part A on its own first. So our solution here, if we're just dealing with part A, what we want to do is we want to find that maximum elastic moment, or our M sub y. So you notice I've wrote down exactly what the variable is and what how it relates back to our problem. So max elastic moment is our M sub y for our problem here. Well, now we ask ourselves, okay, based upon what we're given, what we're looking for, what is a good governing equation? So we can go back into our textbook now and take a look at equation 4.34. Now 4.34 gives us that I over C is equal to 2/3 BC. Now a lot of times we want to leave this as an I over C, and we'll see this in a minute here of why. So we'll solve for that I over C right here, where B is given to us in our problem statement, converted to meters, 50 times 10 to the negative third meters, and C is 60 times 10 to the negative third meters. Now this is why I've already gone ahead and converted to meters in my setup page. So I don't have to do that conversion from millimeters to meters here and accidentally forget to do it and be off by, by a factor at the end there. So we want to make sure that we've done that conversion now that we're in meters. So now that we've done it in meters, we can plug it right back in. So I over C is equal to 2/3, there right there. That's our value for B, 50 times 10 to the negative third, and our C squared, 60 times 10 to the negative third meters squared, so meters and meters right there. So meters times meters squared is meters to the third. So I over C, when we do our math here, multiply by that 2/3, is 120 times 10 to the negative 6 meters cubed. Those are the units that we should expect right there. So this is our value for our I over C. Now, the next thing that we want to do now that we have that I over C is we want to find that max elastic moment, or our M sub y right there. So for our M sub y, we go back to our textbook again, and we see on page 275, we have equation 4.33, which gives us a relationship between M sub y, that ratio right now of I over C, and our sigma y, which is given. So we can now do a plug and chug by write out everything I know over here. So where our sigma sub y given to us in the problem statement is 240 megapascals right there, and our I over C that we've just solved for in the first part of this problem here is 120 times 10 to the negative 6. Units here are meters cubed. So I can plug this value for I sub C in there, and I can plug my value for sigma y right there into that right there. And what I can see now when I plug in, I have my M sub y, or my max elastic moment right here, is equal to this 120 times 10 to the negative 6 meters cubed for this ratio of I over C times 240 megapascals. Make sure we know we're in megapascals, convert to pascals if we need to there. Do our unit conversion. What we end up with is our M sub y is equal to 28.8 when we do that conversion of kilonewtons times meters. So this is our max elastic moment right there. So now that we have that max elastic moment, we can move on to the next part, which what they asked us to solve for here, and find that thickness of our elastic core. So now we recall this as 2 times, because y sub y is half the thickness, so 2y sub y is the full thickness of that elastic core right there. Now where can we get this ratio from? Well, we can get this from equation 4.38 in our textbook here, where we have the m, our moment, is equal to 3/2, the m sub y that we've just solved for right there, times 1 minus 1/3, there we go, y sub y squared over c squared. So we're getting closer there, the squared term, but that's what we want to back out, is that y sub y out of this here. Well, we know our m sub y, so we can plug this in as 28.8 kilonewton meters right there. We have our c value right there that we can plug in as well, so our c value is 0.06 meters right there that we can plug in for that, and we have our m value right here of 36.8 kilonewton meters that we can plug in there. So if we look at that, that's taken care of, that's taken care of, my c is taken care of. Our only unknown is our y sub y. It's squared right there, so we'll have to do a little bit of math. We can plug in those values. 36.8 kilonewton meters equal 3/2, 28.8 kilonewton meters, minus or times 1 minus 1/3. Now this y sub y squared over our c value of 0.06 value right there of meters per units right there. Our only unknown is y sub y. We can plug this into a calculator, Excel, MATLAB, Python, whatever your choice is. Back out that 2 times our y sub y. So we can solve our y sub y and multiply it by 2. So 2 times our y sub y right there is equal to 0.08 meters. So that's where they get our thickness of our elastic core from our general governing equation here, 4.38, where we'd already solved for our m sub y right there, and we had a value for our m right there. So from there, we go to the next part, and we can always reference back to that setup page to make sure we've gone far enough with everything here. So we go back and we figure we still need to find our radius of curvature here, our rho value right there. So in order to do this, first thing we're going to need to do is find our strain in the y direction, epsilon sub y right there. So from Hooke's law, we have the epsilon sub y is equal to sigma y over E right there, where they give us our sigma y in the problem statement, 240 times 10 to the 6 pascals, and our E, our modular elasticity, is given to us as 200 times 10 to the 9th pascals. I can plug that in there, and I can plug this in here, and I can find my E sub y. Once I do that, of 240 times 10 to the 6 pascals over 200 times 10 to the 9th pascals. So our epsilon sub y, my strain in the y direction right there, is 1.2 times 10 to the negative 3rd. Now with that there, I can go to my equation 4.40 in my textbook. And when I have that there, what we can see here is we have my epsilon sub y, this relationship here now, relative to our radius of curvature, our rho. So that's what we wanted. That's why 4.4 is important here, because it related back to our epsilon sub y. Now, maybe you didn't know how to do this part first, but maybe we just saw, hey, we need rho, and we first went down to equation 4.4 and realized, well, there's 2 unknowns, 1 equation, so therefore I'm going to have to use this relationship here from Hooke's law to get my epsilon sub y and plug it into this relationship there, which is more likely the case. But once you've done enough of these problems, you might realize, okay, I'm probably going to need my strain in the y direction in order to solve for my rho. So therefore, I'm going to solve for that first. Either way, it doesn't matter. You could have started with this general equation, realized you had to go back in order to get this relationship here between our stress and our modulus of elasticity to plug in to get that E sub y there. Once we have that, now we have our y sub y right there, which we've already solved for 2 times y sub y, so we have a value for that. So we can put this here and say, rearrange, solve for rho, or radius of curvature, and say rho is equal to that y sub y, which we've already got a value for, over that epsilon sub y that we already have a value for right there. So we can plug this value down in here for epsilon sub y. We can take our y sub y, which is half of our 2 times y sub y, plug that right in there, 40 times 10 to the negative 3rd meters, divided by 1.2 times 10 to the negative 3rd. So we end up with is that radius of curvature here is 33.3 meters. So that solves for 4.5 application problem right there, parts A and B. So now just as a summary to my hand solution here, what I've done here is I have a typed out solution as well, starting here when we went from our maximum elastic moment, used our governing equation 4.34, went from there to equation 4.33 to get our m sub y relationship there, that we plugged this I over C ratio into that right there in order to get a value for m sub y, which we then went to equation 4.38 in our textbook right there, and we're able to get a value out of this now for our y over y right there for the thickness of our elastic core. So again, that was 2 times y sub y there. And then from that there, we're going to take that relationship there in order to plug back in to get our radius of curvature from equation 4.4 right there, 4.40 on our textbook there to get that rho value. So this is just a summary and a good spot to reference back to for all those governing equations if you were to experience a problem similar to this. So now as we continue on with our concept application 4.6, there's two more parts of this problem that they ask us to solve for right here. So we can see down here that I boxed in red right here is after the loading has been reduced back to 0, they want us to find two more things. They want us to find in part C, the distribution of the residual stresses, and D, the new radius of curvature for when it's been reduced back down to 0 right there. So now we'll continue on to application 4.6 solution right here for parts C and D of this right here. So what we have is we have this figure right here with A, B, and C, where A is the stresses at the maximum moment, B is unloading, and C is our residual stresses. For our maximum moment, our M is equal to 36.8 kilonewton meters. For unloading, it's our negative sign convention of that right there. M is equal to negative 36.8 kilonewton meters. And for our residual stresses right here, this is when it's unloaded right there, back down now to 0. So we have 0 moment right there for that right there. So let's take a look at part A for our stresses at our maximum moment right here. So if we know our maximum moment right there is 36.8, we also found that our y sub y right here was 40 millimeters. So we can see right there, if we go up on our y scale right there, there's our 40 millimeters right up to this point here, where our sigma sub y was 240 megapascals. So down here, there's 240 right there, megapascals. There's negative 40 right there. So this right here is our 2 times y sub y going from there to there. Now we can see drawing across that region right there, that is our angle right there for our stresses versus our y value there. Then we can see it goes up now if we refer back to this right here. It's a total of 60 millimeters in each direction outside of that y sub y region right there. So this goes up to 60 straight right there and right there. So this is these are our stresses at the maximum moment right there for our value M is equal to 36.8 kilonewton meters. Then we can go to our unloading phase right here. What we can see is linear across the unloading phase right there. That was the assumption that we're making there, linear elastic. So this comes right down there. There's our negative 60 right there to positive 60 right there to correspond with this right here for our total distance of this member right there. We can see there's our sigma m max right there, and we can do our calculation right here. Our sigma prime m right there is equal to our m, our moment, times that value of c, all divided by our I value right there. So we have that relationship for C over I. We can plug that right in right this here, and we have our value right here for M right there. So we can plug all that in. We find out for that relationship when we plug in our known values is our sigma prime M right there is equal to 306.7 megapascals, which is less than 2 times our sigma Y right there, which would be 480 right there. So we can see right there now we can do this, okay, at our value right here. For that 60 is going to be for 60 at the total M, or sigma prime M right there is 306.7 that we're seeing down here on this x-axis right there. Now, if we were to add parts A and parts B together, like they show right here in this figure right here, our stress at the maximum moment and our unloading right there, we'd end up with C, our residual stresses over here. We see the following graph right there. We still have our sigma sub x on our x-axis and our y on our y-axis up there. And this is for a value of M is equal to 0. So we're at the edge of that elastic core right there. Again, this is our elastic core right there. Total thickness is 2 times y sub y for that elastic core region right there. So we have this relationship right here that our strain in the x direction is equal to our sigma x over E, where we have this value for our sigma x is 35.5 times 10 to the 6 pascals. We know our modular elasticity of the material is 200 times 10 to the 9th pascals. We do that out, and our sigma sub x right here is negative 177 times 10 to the negative 6. So if we want our radius of curvature out of that, our rho value, we can take our value of our y sub y, which we have right here, 40 times 10 to the negative 3rd meters, divided by that epsilon sub x right there. And what we can find now here is we can get a rho right there for when M is back to 0 after the unloading of 225 meters. And just a side note, if you're asking where these values came from, it goes, again, like I just mentioned here, by adding these two together. So if you have a negative 240 and a positive 306.7, that's where you end up with this 66.7 there, and the rest are corresponding to doing that same thing again, where you add, again, your part A, the stress at the maximum moment, with your unloading right here, and that's how you get your graph C right there. So next we're going to move on to the topic of eccentric axial loading in a plane of symmetry right here. So when we think about this right here, we have stress due to eccentric loading found by superimposing the uniform stress due to the centric loading and the linear stress distribution due to pure bending moment there. So our governing equation for that right there The formula here is our sigma sub x is equal to our sigma sub x centric plus our sigma sub x bending right there. So there's an equation for what we said in the wording up here. And what we have from that there is this is equal to now down here, we have equation 4.50 where we have this relationship P over A minus our M sub y over I is equal to this sigma sub x, which again was the summation of the sigma x centric plus sigma x bending right there. So that's our relationship when we go back to our textbook to equation 4.50. So if we go back over here now to our figure in 4.39, we can see in part A on the top up here, what we have is we have this member with eccentric loading right there. So you can see our loads right down here. We have a P and a P prime located at A and B right there. And we can now see we have our point C up here. Here's our centroid up there, a C right there like that. So we can see these are down here in this line right here, not going through our C right there. Now from this, if we were to section this off as C, we get down to part B of this figure right here. So this is the free body diagram of the member with internal loads at that section C. So we section it C right there, and now we can see that internal loads right there. There's our force right there, and there's our moment right there. And we have some distance between this force right here and where we're taking our moment about C, shown as D, as our distance away from where our load P is applied down here. Now, a thing to note, these results are only going to be valid if the stresses do not exceed the proportional limit. These deformations are going to have negligible effects on the geometry, and stresses are not evaluated near points of the load application. So you can see our relationships down here for eccentric loading right here. So our F is equal to P. So going back up here, this F right here in our free body diagram is equal to our P over there. And we could do this out with our equilibrium equations to prove this to ourselves. And we could also see that our P, or M right here, our moment right here, M, this is equal to our P right there, because P is equal to F, times this distance right here away from there, that perpendicular distance. So again, this is for our eccentric loading to get these values for our M and our F from our free body diagram. And now we can go down to figure 4.141 right here, where we can see that these stress distributions for eccentric loading obtained by superimposing the axial and pure bending distributions right there. So again, we can go back up to this governing equation that we have up here, and we can say, okay, there we have our sigma sub x for our centric, sigma sub s for our bending is equal to our sigma sub x right there for this general governing equation right here. And again, when we plugged in to equation 4.50 right there, we can plug those in if we had some numerical values. We can see graphically right here, we can see our load distribution right, or sorry, our stress distribution right here, uniform for this first part in A. Adding it over here to our bending moment right here, we're going like this right here for our distribution of stresses right there. And then last, you can add those two together in order to get part C right there, where we're looking for our stress distribution over the entire member right there. So now I want to take a look at unsymmetric bending right here. So this relates back to the section 4.8 in your textbook right here. So as we're looking at this right here, let's first take a look at the analysis of pure bending that has been limited to members subjected to bending couples acting in the plane of symmetry right here. And we can see right here, this is illustrated over here in figure 4.44. So the members remain symmetric and bend in the plane of symmetry right there. So we can take a look at that in case A and case B for this over here, two different examples of that right there. What we can see is that the neutral axis of the cross section is going to coincide with the axis of the couple as well. And again, this is illustrated back over here in this diagram. But then now let's consider situations in which the bending couples do not act in the plane of symmetry right here. So now we can see this right here illustrated in figure 4.45, where now we can see that neutral axis right here, and then we can see our bending moment right there, right there. So we can see that these do not act in the same plane of symmetry right there as we've seen before. So with this right here, for what we're seeing in this case here in figure 4.45, we cannot assume that the member will bend in the plane of the couples right there due to that. In general, the neutral axis of the section will not coincide with the axis of the couple. So two different situations to deal with right here for unsymmetric bending when we take a look at that. So continuing on with the topic of unsymmetric bending right here, let's take a look at figure 4.46. So in this figure here, we see a section of arbitrary shape right here up in the diagram above, where the neutral axis is going to coincide with the axis of the couple M right there. So there's our neutral axis going across right there. And you can see it right here, it coincides with our axis of the couple M right there. Now within this, if this were a problem that we were working on here, maybe they'd ask us to determine the conditions under which the neutral axis of the cross section of arbitrary shapes, there's our arbitrary shape above there, is going to coincide with the axis of the couples shown. So how do we go about this here? Well, first let's take a look at the resultant force and the moment from the distribution of the elementary force in the section couple, they must satisfy this relationship down here that we see right here. So our f of x is equal to 0, which is equal to our m sub y. Now with this, we also see that our m sub z must be equal to m, which is equal to our applied couple. So these are the elementary forces in the section right here. They must satisfy these relationships right here. So now if we were to take a look right here, we can see here's our individual element over here, our individual force element, our sigma x dA across our area of that small element right there, and our sigma x of that right there. So now with this right here, for this f of x, if we wanted to do this over the entire arbitrary shape of this element right here, we need to do a summation of those right there. So we'd say, okay, our force in our x direction, which is equal to 0, from this case down right here for m is also equal to our applied couple right there, is equal to the integral. So we're going to integrate, sum up all of those individual force elements right there, our sigma x dA right there. So we do that in and we can plug in a relationship for that right there. And this we can see is now equal to the integral of our negative y over c times our sigma sub m times dA. So what we've done right here is this is our sigma x from our relationship that we've seen previously in this module right here. We replace that with our y over c, our negative y over c times our sigma sub m. I see our dA is still our dA there. Or when we do this out, we can see that this is equal to 0 is equal to our integral of y dA right there. Now we know that our neutral axis passes through the centroid right there. So we have this relationship down here. That m is equal to our mz right there. So m is equal to mz is equal to that integral of y times right there. So force times that perpendicular distance. There's our force from above up there. We can plug that in right there. Now we're multiplying it through by that distance y right there. Plug that in to get our moment right there. So we can then reduce this down and say that m is equal to our sigma sub mi over c right there, where I is equal to I sub z, or our moment of inertia right there. So this defines our stress distribution. So this all leads us up to, in our textbook right here, equation 4.51. So I suggest checking back on there, going through this derivation, showing how we obtain this relationship that we see here in equation 4.51. We say 0 is equal to my is equal to the integral of z sigma x dA is equal to, reduce that down, plug in our known values there. For our sigma x right there, we end up with our integral of z times our negative y over c times our sigma m dA right there. Or right there, we can put this down in with our product, with our moment of inertia equation relationship right there. 0 is equal to integral of yz dA, which is equal to our I and the yz, or our product of our inertia right there. This is a couple vector and must be directed along the principal centroidal axis. So now as we continue on with unsymmetric bending, we want to take a look at the case where we're dealing with unsymmetric bending with a bending moment not in the plane of symmetry right here. So for this, we're going to use the fact that superposition is going to be applied in order to determine stresses in the most general cases for this unsymmetric bending. So with this here, we're going to reference our equation 4.52 in our textbook here, and we're going to resolve the couple vector into components along this principal centroidal axis right here. So we do that there, and we resolve them into their components right here. We're going to resolve them into the z component and their y component. So we can do out some basic trig, and we can go back to this figure 4.49 and see, okay, there's our angle theta right there. So in our z direction, we have m times the cosine of theta. In our y direction, we have m times the sine of theta. Break them down in terms of our y and our z components right there. So that's where we come up with this relationship in our 4.52 equation. Now from there, we can go to equation 4.55 and superimpose the component stress distributions there. So we see that our sigma sub x is equal to, we have our m sub z times our y, the negative value up front, over our I sub z, and our m sub y times y over I sub y there. So now if we're along the neutral axis, what we can do is we can say, okay, our sigma sub x is equal to what we just saw above there, and then we do and break these down into their components right there from this relationship in 4.52. So essentially we plug that relationship from 4.52 into mz and my in equation 4.55. We do that, we see that our sigma sub x is equal to 0, is equal to a negative m times the cosine of theta over times y over our I sub z, plus m times the sine of theta times y over our y sub z for our m sub z and our m sub y plugged in respectively right there. So from there, what we can do is we come down, take a look at this figure 4.54 for the neutral axis for unsymmetric bending right there. So you can see your neutral axis right there. So from our neutral axis, we have this angle phi right there. So our tangent of phi is equal to our y over z when we do that out there. Well, now we can plug in for that and relate it back to our theta term, which is for our moment right there. And we can say now from that right there, we now have the tangent of phi is equal to y over z, which is equal to our I sub z over our I sub y times that tangent of our theta term right there. Now, a thing to note, we go back over here to 4.51. This m sub z that we've solved for up here in 4.52 right there, this acts in a plane that includes the principal centroidal axis, bending the member in the vertical plane right there. So you can see there's your bending moments right there as it acts along that axis right there, along our y. And then we can see down here in 4.52, my right there that we solved for up here, this acts in plane that includes a principal centroidal axis right there. So we can see that plane right there. You can see the bending of the member in the horizontal plane right there like that. So just a visual representation of your mz and my. We broke down those components from this figure 4.49 in the top. So now let's go through a practical example right here. So let's take a look at concept application 4.8. Within this problem, they give us a problem statement down here and an initial given diagram as well. Within the problem statement, they tell us that a 1,600 pound-inch couple, we can see that up here, is applied to a rectangular wooden beam in a plane forming an angle of 30 degrees with the vertical. So we can see it's out of plane of that vertical right here by an angle of theta equals right there of 30 degrees like that. Now within this here, they want us to determine two different things. In part A, they want us to find the maximum stress in the beam. And in part B, they want us to find the angle that the neutral axis forms with our horizontal plane. So we need to figure out where that neutral axis is and how it corresponds to our horizontal plane there. We can see if we come back up to our diagram, we have our overall dimensions. The height is 3.5 inches. Our width is 1.5 inches right there. So now we've had an opportunity to kind of look through the problem statement, look at the initial given diagram right here, and from there we can go through and start forming a procedure for analysis and start thinking about some of the governing equations we might want to utilize for our solution. So we take a look over here. First thing that we want to do is we want to resolve the couple vector into components along the principal centroidal axes and calculate the corresponding maximum stresses. So in order to do that, we need to find our m sub z, m sub y, break it down in terms of its components right there. So m sub z is we take that moment m times the cosine of phi. And for m sub y, we take that moment m and multiply it by the sine of phi to get its components right there. Next, what we want to do is combine the stresses from the components stress distributions there. So we can do that by saying our sigma sub x, we've seen this equation before in previous slides right there in this module, is equal to our m sub z times y over I sub z plus our m sub y times z over I sub y. And last, that will give us what we asked for in part A, the maximum stress in the beam from those breaking down those components right there. Then in the second part, part B, our plan of attack and governing equation is going to come from determining the angles of the neutral axis right here. We have the tangent of phi is equal to y over z, which is equal to our I sub z over I sub y times the tangent of theta right there. So that'll be our governing equation for part B to determine the angle of the neutral axis. So as we jump into our solution here for this here, first thing that we want to do is resolve the couple vector into its components and calculate the corresponding max stresses right there. So first part of that is to resolve these into their actual components right there. So we can see we want to find our mz and our my from those governing equations that we saw earlier right there. So we can take and break them down to their components. Now, if we look over here at our diagram, I really like what we've done over here. We've broken it down and we've got a visual 2D representation looking at that triangle. We can look at our trig right there, say, okay, if I want that moment around z right there, that's going around this z-axis right here. This is the angle of 30 degrees right there. If I want that component in the z direction, I can do out my trig. I can remember SO, CA, TOA, bring it back all the way from high school or junior high school math, plug that in there, and we can find out that we can see our m sub z is equal to our 1,600 pound-inch right there times our cosine of 30 right there. So we can plug that in. That gives us a value now, we get a numeric value for m sub z when we break that into its components right there of 1386 pound-inches. Now we can do the same thing for our m sub y. There's our m sub y there. So if we want that component right here of this right here going along our y-axis right here, well now we're going to say it's the sine of 30 rather than the cosine of 30. So we say 1,600 pound-inches times that sine of 30 right there. We do out our math right there and we get our m sub y is equal to 800 pound-inches there that we can plug in. Now next, in order to get our sigma, we have our general governing equation we've seen before. We have our m times our y over our I. So we realize we're going to need to get our I values here in the z direction, in the y direction right there. 1/12 base times our height cubed right there is our general equation. But now remember, our base and height are going to alternate whether we're looking at our y-axis or our z-axis there. So this is a general equation you can get for this rectangular shape. We can go back to our appendices or some of our previous textbooks as well to get that governing equation. So in our z direction here, we have 1/12, our base right there, which is our 1.5 right there. So if you recall, our 1.5 goes from A to B right like that there. So then we can say, okay, along that times our value for 3.5 right there, our total height right there, squared or cubed right there. So our I sub z right there is going to be 5.359 inches to the fourth. And then we do the same thing for I sub y, 1/12 now of our value right here, 3.5, as that alternates now right there, times our value of 1.5, this distance right here, cubed right there, is equal to 0.9844 inches to the fourth right there. So from that information, now we have a value for our mz, my, iz, and iy. So now we can go ahead and calculate the largest tensile stress due to our mz right here, which is going to occur along AB right there. So our general governor K, we're saying this is equal to sigma 1 for that maximum tensile stress due to our mz, is our mz times y over iz right there, where these are all known values we've calculated now. I can plug in my mz was 1386 pound-inches. My y was 1.75 inches. You can see that right there. And now we have our value for our I sub z that we've just calculated above right there of 5.359. We do this out, and sigma 1 is equal to 452.6 psi. Now we calculate next the largest tensile stress due to my, which occurs along A sub d right there. So there's our A sub d right there like that. Now this is equal to our, say, our sigma 2 is equal to my times z over our iy, where my we have from above right here, 800 pound-inches that we can plug in. Our z value now here, this is our 0.75. We go along that axis there. All over our I sub y, which is 0.9844 from this right here in inches to the fourth. Do out our math here, and we end up with 609.5 psi. Do out your unit analysis. Make sure you really are getting psi as well as a double check. So from that there, the largest tensile strength due to the combined loading occurs at A. And this right here is going to be our sigma max equal to sigma 1 plus sigma 2, or those two values of 452.6 psi plus 609.5 psi. We sum those up, and our sigma max right here is 1062 psi, which was what they'd asked us to solve for in the first part of the problem. So now that we've completed the solution for part A, we move on to part B. We can go back to our setup page. Realize in part B, they asked us to determine the angle of this neutral axis right there. And this neutral axis, we already found our governing equation back in our procedure for analysis. Our tangent of theta is equal to Iz over Iy times the tangent of theta, which we found which is given to us as 30 degrees in the problem statement. We've already solved for our Iz and our Iy. We can straightforward plug and chug those ones in there. So our tangent of theta is simply equal to 5.359 inches to the fourth over 0.9844 inches to the fourth times the tangent of that theta term is given to us in the problem statement. So our theta, or the angle of our neutral axis, is now found to be 72.4 degrees. And then down here in D, we can see we have the cross section with the neutral axis and our stress distribution right there. So there's our neutral axis right there. And we see our stress distribution as we come across this right here. Negative 1062 psi there, negative 1062 psi, or positive 1062 psi there. Next, I want to take a look at the general case of eccentric axial loading. Now for this here, what we want to do is consider a straight member that's subject to equal and opposite eccentric forces right there. So we can see down here, here's our eccentric forces. They're not going through the center right over here. This makes it eccentric right there. And you can see that these are both equal and opposite P and P prime. Now with this here, the eccentric force is equivalent to the system of centric forces P and the two couples Mx and My, where P is going to be our centric force. Our M sub Y is going to be given by P times A right there, which is our P right there, times that distance away right here, right there. There's our A from the central axis right there to where that load P is right there. And our M sub Z right there, which is going to be load P right there, that same load P, times this distance B, which goes up to our Z axis right there. So that's where we come up with those moments right there from that centric force P right there. And their distances, their perpendicular distances, back to both our Y and our Z axis right there. So that gives us our M sub Y and our M sub Z right there for our moments. Now we can go and take a look back at that principle of superposition right there. And from that, we can see that our combined stress distribution is given by the relationship shown in equation 4.58. Now in this equation right here, we have the sigma sub x is equal to P over A right there, minus that M sub Zy over Iz, plus M sub Yz over Iz right there, which is, again, same what we have here. The eccentric forces is equivalent to the system of centric force and the two couples. So there's our force and the two couples right there, broken down in terms of our stresses right there. So we have our load and those two moments right there in order to produce our sigma sub x, which we see in equation 4.58. Now for the case right here, if the neutral axis happens to lie on the section, it may be found from this relationship down here that our P over A relationship right here is equal to our Mz times Y over our Iz minus our My times Z over our Iy. And this relationship can be found on page 309 of our textbooks. Now, if we go back over here to this figure 4.56, we can take a look for eccentric axial loading right here. We already discussed part A right here. This is the axial force applied away from the centroid section. So we can see right there, there's our section centroid right there at C. We can see this load is a distance A away from our y-axis where the centroid is, and a distance B away from our z-axis where that centroid is there. And that is where the location of that load is to make it our eccentric load right there. And in part B down here, what we can see now in this diagram right here is the equivalent force couple system acting at the centroid. So that's where we use those relationships we just discussed right here in 4.58 and on page 309 of our textbook right there to bring it back over here onto this right here. So it's the equivalent right here of this force P acting at the centroid and these two moments My and Mz acting along those axes. And again, these are equal and opposite right here as we see on the other side right there, P prime, My prime, and Mz prime as well.